Okay, so a very common thing you're going to encounter in Math 123 is changing between bases. 123 is an adventure, to say the least. There's a lot of abstract ideas in it, and it's good to just be aware of the different things that you could encounter. And one of them is this base idea. So just to give you a feel for what bases are talking about, when I'm counting, I start with 0, and then there's 1 object, 2 objects, all the way until I get to 9 objects. And we're so used to seeing the base 10 system that we know the next thing that comes is 10, represented like this, meaning that the rightmost digit drops back to 0 and the next one over increases by 1 unit. If I was down here at 19, it would repeat that same process where this goes back to 0 and the next one increases by 1, where this represents 2 groups of 10 and this represents 0 groups of 1. So that's the idea of a base system. We're used to seeing the base 10 system, but in Math 123 they changed that up, and they want you to do stuff like this, where you need to convert one number, which is 16 objects, and using different symbols you need to represent that same idea. And here what we're going to do is convert it from base 10 to base 3. So there's a couple of different ways you can approach this. The first way is to just begin by labeling all of the different placeholders. So I'm just going to draw some blanks here, and underneath them I want to put in the corresponding place value that they would hold. Normally it would go, okay, that's 1, then you would have 10 and 100 and 1,000, meaning if I put a 3 right there, that represents 3 groups of 1,000 and 2 groups of 100 and 7 groups of 10 and 8 groups of 1, or whatever it is, the numbers that end up happening. But what's happening here is that we're changing bases. We're not increasing by 10 each time like we would in the base 10 system. Instead, what we're doing is increasing by 3 each time. So this would be the 3's spot. And the next one over would be 3 times larger, which is 9. And the next one over would be 3 times larger, which is 27, and the next one over, and so forth and so forth. So the shortcut you can take is you always start with your base, and you begin with it being raised to the 0 power. Any number to the 0 power is 1. And from there, all you have to do is increase your power each time as you go left. So I've just labeled some placeholders, and what I need to do is use these symbols, these objects, one way or another so that I represent 16 by the time I'm done. So I start with the leftmost side, and I go, how many times will 81 go into 16? Well, it doesn't. Not at least once. So I can't use that placeholder. Okay, well, what about 27? Same problem. 27's over 16, I can't use it. Okay, will 9 go into 16? Yes, it will. How many times? Just once. So that's what I'm going to write there. I can have one group of 9 in the 9's place. And I want to know how much is left over. Well, I multiplied those and subtract them, and I find that I have 7 left over. So from here, I want to say, okay, using those, how many times will 3 go into 7? Well, it goes in twice, so that's what I'm going to put in there. You multiply back and you subtract, you get 1, right? And now, this is where I can end it. I want to know how many times 1 goes into itself. Well, that one's easy, just 1 time, and when I multiply back, I have nothing, which means it's actually a whole number. It's an integer. So to represent 16 base 10 into base 3, I would need the digits 1, 2, 1. And just to explain what this really means, it still represents 16 objects. There is no difference between this guy and this guy. This one just requires different symbols than this one does. But if I were to break this down, this is the same thing as having one group of 9. This is the same thing as having 2 groups of 3, and this is the same thing as having one group of 1. And when I add those together, you can see that I would get 9 plus 6 plus 1, which gives me 15 plus 1 is in fact 16.